This video is really more about proving the Pythagorean theorem, but I thought I'd throw in a statement here that most people do remember the Pythagorean theorem pretty well, or at least the core of it, the a squared plus b squared equals c squared statement. Many people don't bring in the fact that it's really more specific than that. The Pythagorean theorem itself states that if you have a right triangle with legs of length a and b and a hypotenuse of length c, then it would be true that a squared plus b squared equals c squared. So it's really more that these two things are paired together. You must have a right triangle to even talk about it. Otherwise, it feels a little weird. What I've done is I've drawn a really poor sketch here of what was supposed to be a square with another square inside of it, and I've broken down all the lengths in a certain way. The inside square has all sides of length c, and this outside square has side lengths a plus b. So maybe I should make that note here. A plus b. So each of the sides of the outside square have been intentionally chosen and labeled in the way that they have been so that we can actually kind of relate back to the values that are up here at the top. What I know is that the area of the overall square, so we'll say area of large square, the area of that huge square, the entire thing, should equal the area of the little square plus the area of all four triangles. So that's something that I think most people can agree with when you take a look at this. The entirety of the square should equal the smaller square plus all those little triangles, all four of them. Well, I know that the area of the big square can be represented by a plus b times a plus b, because it's length times width, or side squared, depending on how you want to look at it. So a plus b times a plus b would be the area of the large square. The area of the little square would just be c times c, or c squared. That's why it's called squaring something. And then the area of all four triangles, well, this is going to be adding in four triangles that are all 1/2 their base times their height, which is a times b. So here we have c squared plus 4 times 1/2 ab. Again, where 1/2 ab is the area of one of these triangles here, with a being the base and the b being the height this time. And then we just need to do a little bit of work here. We've set up a situation that must be true based on our rules of geometry. In fact, I'll be releasing a video on area a little bit. Here we have a plus b times a plus b. This is going to be a squared plus 2ab plus b squared. So a times a is a squared. B times b gives me the b squared. But then I also have b times a and a times b that will happen, and they're happening twice basically. So there's two of them. Now that's all still equal to c squared. And this should be a good point to note. We have a squared, b squared, and c squared already in the problem, so we know they're connected somehow. But this 2ab is a little messy here, and we want to kind of maybe hope to get rid of it. Well, if you notice, on this side, 4 times 1/2 is 2, and I see 2ab on both sides of my equation. So if I subtract the 2ab from both sides, we find out that in fact, a squared plus b squared does equal c squared for this circumstance. And if you look up here, the idea is that this is a right triangle here with a, b, and c, and we've just shown with no numbers included, we haven't had any measurements given to us. We know that no matter what values we've chosen for this square, a squared plus b squared would have to equal c squared, no matter what size these squares end up being. And that's a basic proof of the Pythagorean theorem.